Hello, this is Wei Zhang from Clemson University. Here is a presentation about coseismic and long-term changes of site response on liquefiable sites, a case study of the Onahama port area in Japan. Here is the presentation outline. First, let's look at the definition of liquefaction. Liquefaction is a process which water-saturated sediment temporarily loses strength and acts as a fluid under earthquake loading. Liquefaction can impact the environment from small scales to large scales, such as sand boils, ground deformations, and landslides. Liquefaction hazard can cause huge economic loss, as shown in New Zealand case. The most famous liquefaction case history is from 1964 Niigata earthquake. Severe liquefaction induced ground deformations, teared several apartment buildings. A seismograph at the basement of one building recorded the forced ground motion affected by liquefaction. It shows clear evidence that liquefaction can modify ground motions. A numerical analysis suggests the liquefaction can amplify the long period spectral accelerations, and while it amplifies the short period spectral accelerations. Current seismic design code recognizes the complex site effects on liquefiable sites and require site-specific analysis for site amplification. We summarize the two main challenges for site response analysis on liquefiable sites. The first one is the lack of seismic observations in liquefied stations. According to one of our recent work, there are only 44 liquefied recordings in the world. The second challenge is the computation difficulty of soil liquefaction behavior. From this shear stress and the shear strain plot, we can see at least 2 points. First, the shear stiffness decrease with shear strain increase. Second, the shear stiffness can be very high at large shear strains due to the cyclic soil behavior. Moreover, the site response of liquefiable soil can be affected by the generation and dissipation process of pore water. Hence, this study aims at systematic quantification of coseismic and long-term changes of site response on liquefiable sites. The result could be used as the basis for physical and data-driven ground motion predictions for liquefiable sites. We select Onahama port area as a study site. It's located in Fukushima Prefecture, Japan. This area consists of 2 accelerometers located at the surface and 11 meter deep. During the 2011 Tohoku earthquake, liquefaction is observed near this area. This area recorded extremely high ground motions with peak amplitude approaching 2G. The high-frequency acceleration spikes are suggested to be induced by subsurface soil liquefaction behavior. Further investigation suggests the medium dense sand between 1.3 and 4.0 meter deep are liquefied during this event. We collect in total 1,238 earthquakes recorded by Onahama port area between 1995 and 2020. This slide shows the spatial and the temporal distribution of the collected seismic data. We apply the sliding window approach to track the coseismic and long-term change of spectral ratio using paired surface and borehole recordings. The method consists of 3 main parts. First, the seismic phase selection. We select the pre-event noise P and the S phases using generalized phase detection code proposed by Rose. And we decided the cold phase start time as 2 times of the S wave arrival time. The second part is applying the sliding window to divide each earthquake recording to many traces. The window length is 6 seconds and the moving step is 2 seconds. The dashed line on the right top figures show 3 demo traces in a recording. The third part is to calculate the spectral ratio calculation. First, we remove the mean value of traces and apply table to both ends, and then we we compute the Fourier amplitude spectrum and apply smoothing. Then we compute the spectral ratio following this equation. This plot shows the spectral ratio of three traces of the different phases during the 2011 Tohoku main shot. We track the temporal change of spectral ratio through the image with the horizontal axis as the trace window time, and the vertical axis as the frequency, color as the spectral ratios. From the image of the 2011 Tohoku main shot, we observed that there are two high spectral ratio bands. It's consistent with the left plot, where we see two peak spectral ratios and the two peak frequencies. It's marked by the circle and the square here. Second, we can see the peak frequencies and the peak spectral ratios gradually drop and then recover during the main shot. The third point is a short-lived frequency and the spectral ratio increasement observed near the PGA occurrence time, which is related to the liquefaction behavior. We can also observe this change when we extract the peak frequency and the corresponding peak spectral ratio using the scatter plot. We found the higher peak frequency is easily affected by the strong ground motions. Then, hence, we analyze the peak frequency, higher peak frequency change as a measure for the coseismic change. We define a measure called the maximum peak frequency drop to quantify the coseismic change of peak frequency. It's defined as the ratio between the reference peak frequency minus the minimum peak frequency among all S-phase traces in a earthquake record, and then divided by the reference peak frequency. We fill out the other 15 strong ground motions that did not trigger liquefaction and conduct the same analysis. We found the maximum peak frequency drop of liquefaction trigger event is 65%. That is significantly larger than the values of other non-liquefied events. The cyclic mobility spikes induce peak frequency increasement about 40% during the Tohoku main shock. This image shows the post-liquefaction short-term change of spectral ratio using the recordings of the Tohoku main shock and the 9 aftershock recorded within 5 hours. We observed the two stages of logarithmic recovery of peak frequency after its sharp drop during the main shock. The first stage is a rapid recovery to 80% of reference value within 100 seconds. And second stage is a slow recovery to a reference value within a half hour. This slide quantifies the long-term changes of spectral ratios. We average spectral ratios for events before Tohoku and the Tohoku main shock and events between 2013 and 2020, and get these three curves. We find that both the higher and lower peak frequencies drop during the Tohoku main shock and then recover to pre-Tohoku level. We find a periodic trend of peak frequency using spectral ratio data of events between 2013 and 2020. Peak frequency varies between 11 and 15 Hz, with average value of 13 Hz. The changing period is about 1 year. We select part of the record for detailed analysis. We find the peak frequency fluctuation correlates well with the rainfall data recorded from a nearby station. Peak frequency increase during the rainy seasons, which implies the seasonal change of groundwater table may affect the site response of shallow soil sites. Here is a summary of the main conclusion of this work. Thank you for your time. Please let me know your questions.